Okay, hello guys. So first we're gonna do a little bit of review from last week about the decision trees, like the coding portion, because we didn't really get to look at that. And then when our vice president has like a couple announcements on projects that the club is doing this year, and then I'm gonna go on to ensembling today. So first is you guys remember the stuff we did about decision trees last week, right? Like how they work and stuff. Yeah, okay. How when you make a decision tree, how do you know which things to split upon? If I give you like a data set of features 1, 2, and 3, how do you know how to split upon which feature? You guys remember? Anyone know? Yeah.
Which one has the lowest entropy?
Yeah, lowest entropy, you can use Gini index, either one of those works. What are the two main types of, what are the two components of a decision tree? There's two types of things you can have in a decision tree. One of them is very obvious because it's also on normal trees. It's not branches. Leaves, yes, decision trees have leaves. They have leaves and internal nodes. They're the two parts of decision trees. Yeah, that's pretty much covers the main stuff about decision trees. We had a little bit more in depth on like the mathematics behind the last week too, but this is just the coding portion, so you don't need to know that for this. So let's look at our data first. Okay. So our data set is this. What we're trying to do is we're trying to predict whether or not someone is drunk based on the following features. Their favorite number, the type of alcohol they drink, how many shots they took, and what year they are. These are our features. So right off the bat, if you're just looking at this, who thinks that favorite number is going to be an important feature to split upon? Think about what that means. If you split upon a feature, that means that there's a that there is a low entropy, which means low variance between the relationship of the favorite number and whether or not the person is drunk. So who thinks favorite number is going to be useful as a feature? No one. Okay. How about the type of shot, the type of alcohol they drink? Yes. Okay. How about the number of shots they've taken? Does that relate to how drunk they? Yes. How about what year they are? No, not really. Okay, so this is what we have. Now, what else do you guys notice about this data set? So when we looked at stuff last week, all of our data was primarily true or false, like in the heart attack example. Each one of our category was true or false. In this case, we have a true or false column, the drunk column. But the drunk column is our target, so you cannot train upon this because then there's no point. So, I mean, I guess you can, but you have things like year, we have things like type of shot. These are categorical names. So how do you guys think we'll go about this for the decision tree? Because decision trees only understand numbers.
Splits in all the categories, and then from there, once you've split in the separate kinds of categories, filtered by number.
Yeah, we can map them all to numbers. So let's import our data. That's exactly what we do. So we have first, second, and third years. We map them to numbers. We map yes and no to numbers. And we map all the different types of alcohols to numbers as well. So now we're going to define our features. So this is basically telling the model what can we use to predict whether someone's drunk or not. What's our X? In this case, like we said before, it's favorite number, type of shot, number of shots taken, and the year. And our Y is whether or not the person is drunk. So this right here, decision tree classifier, is scikit-learn's sort of version of a decision tree. So in practice, when you make a decision tree, you don't need to code one up, make its classes and everything by yourself. You can just import this from scikit-learn. And then to make it train, you can use fit, and you put in the X and you put in your Y. To do this, it's done training. So now let's look at our tree. Plot tree is a separate thing you can import to look at the tree. Let me zoom out. It's already. So this right here, shots taken, this means that this is our feature. It's our root. It's the feature that had the lowest entropy out of everything. This is the most segregating feature. Yes.
What's entropy?
So last week we went over ways to measure how to know which feature to split upon. Entropy is basically a way to measure that. It's saying if I split my data based on this feature, in this case shots taken, how much variance do I have in each one of these groups? Ideally, you don't want any variance in the group. If you split this data, both sides should be a perfect split of the data. Like you should be able to say that if I have less than 6.5 shots, I am not drunk. And I have more than 6.5 shots, I am drunk. That's a perfect split. And so what you want is you want a low entropy in both parts. You want low variance. You want the data on both sides to be about the same. That's what entropy is. So far, does anyone have any other questions about decision trees? We're good? Okay. That's our first feature. So now we have two separate groups of data. We have everyone that takes less than 6.5 shots, which is true. Everyone who takes more than 6.5 shots, which is like the false. Oh wait, no, I take that back. Sorry, I got it mixed up. So true is less than 6.5, false is greater than 6.5, not greater than equal to, just greater than 6.5. So look at here. See how the Gini is just 0 and there's nothing below it? This is a leaf. This means that everyone who took more than 6.5 shots is drunk, regardless of what they drank, regardless of the year, regardless of what their favorite number is, they're drunk, which makes sense intuitively. However, if you go here, we have to split again because right here our Gini index is 0.32. This Gini and entropy are very similar ways to measure the same thing. So a Gini of 0.32 means that out of our values, we have 4 positive and 1 negative. And we have 4 people that aren't drunk and 1 person who is drunk in this less than equal to 6.5 criterion. So now we have to split again. And we split again on type of shot. This is the type of alcohol. Look here, but this is a number. Remember earlier when we mapped all of the types of shots to numbers? That's what this is here. So if you go back up, 1 is Malibu, 0 is Grey Goose. So if you took Malibu or Grey Goose, this should be true. That means you're drunk. Versus if you're here, it's positive, negative. Let me think back. Okay. If you took Grey Goose and Malibu, which means you're less than equal to 1.5, that means you're not drunk. You're in the negative, so it's positive, negative. So you're like the 1 person who is not drunk. Versus if you took any of these, that means you are drunk. And so you're on this side over here. And so now our Gini is 0 again, which means that we have a perfectly segregated split based on the type of shot criterion. Does that make sense to everyone? Yes.
Can you please explain the decision tree?
Yeah, so basically all the decision tree is, it's a very, very simple machine learning algorithm that basically sort of works as a bunch of if-else statements. You have a bunch of this data here, and we have our target, which is typically some sort of binary of true or false. In this case, it's drunk or not. And what you're trying to do is you're trying to take your data to model this problem, which is someone drunk or not, based on this information that you know. So this is our information that we know, and we're trying to see whether someone's drunk or not. And so what we do is our goal isn't to use all the features. Our goal is simply to use the best features. And in this case, the best features were shots taken and type of shot, which intuitively makes sense. Yeah. And so all the decision tree does is, given the data, it's trying to get an accuracy as close to 100% that it possibly can by choosing the features that you split upon that have the lowest Gini or the lowest entropy. An example I would say of this is, let's say you're trying to choose what to do every day. You wake up and you have a couple of choices. You can go to class or you don't go to class. Each one of these decisions leads to some outcome. You can model your entire day with the decision tree, which your binary could be whether or not you get a good grade, right? You could say that, should I go to class or not? Yes or no. And it leads to some sort of output about you getting a 4.0 GPA. That makes sense? Like the decision tree is sort of like taking a decision every step of the way, and that leads to some sort of class that you end up in. It's like a flow chart. Does that make sense? That's all a decision tree is. Conceptually, that's how it works. Yeah, so that's the coding portion. There's other interesting things too. When you make a decision tree classifier, there's a lot of different modifications you can do to it. So right now, the default way to split up a feature is using Gini. You can use entropy as well, or you can use log loss. These are all different ways to split. Another thing is the splitter. So remember I told you that we want to use whatever is the has the lowest entropy or the lowest Gini. You can not do that. The default is best, but you could do a random split too. Your decision tree could be purely random. Now I've been thinking, why would you do that? Like, do you guys have any ideas? Like, why would you want to do a random split? Think about it. Even though it doesn't sound intuitive, even though it sounds like a bad idea, why would you want to do a random split? Sometimes. Yeah.
To reduce bias.
Yeah, or it's to reduce overfitting. If you always choose the best feature every single time, you might get very overfitted to the data. Like if you look down here, there is one person who isn't drunk based on this type of shot. What if in our testing set, there's a person who gets that gets drunk off of Malibu? According to this, if they had less than 6.5 shots and they drink Malibu, they cannot be drunk. But what if they are? What if we did a random split here instead and we had a more even amount, like 2 here and 3 here? A random splitter would allow you to reduce for overfitting by occasionally choosing the class or the feature that isn't the best sometimes. What else do we have here? We talked about this briefly at the end of our presentation last week. Min samples leaf. Min samples leaf is a similar thing that random splitter does. It requires that in order for this to be a leaf, there needs to be a certain amount of data points at that spot. So in our tree, we have one person at this leaf. If I set that to 2, I have to choose a different feature, even though that feature might lead to a greater depth. I need to have 2 people at that feature, again, to avoid overfitting. Another one is called max depth. Max depth does a similar thing. It says that my decision tree cannot be too overfitted. Even though my accuracy might not be 100%, it's 100% here because we have a very small data set. Even if our accuracy isn't 100%, I don't want a decision tree with a depth of 100. I can have a decision tree with a depth of 10 and accuracy of 80%, but I'm okay with that because it's less overfitted to the data. Does that make sense? The idea of max depth? Yeah, that's pretty much, I think that's interesting. Max features as well. If I have a lot, let's say I had like 10 different features here, I don't want to use all 10. I just want to use maybe 2 of them in my entire decision tree. That is also okay. So this is basically how you code up a decision tree classifier. Even though decision trees might seem kind of dumb and naive and like, oh, why would I ever use this? They can be very, very useful in some applications. So that covers our coding example for decision trees. Anyone have any questions on this coding example? Okay, we will go on to ensembling then. So last week we went over decision trees. At the very end, we went over XGBoost, which was kind of like a decision tree. We trained one decision tree, and the rest of them were trained based on the mistakes the previous one made. It's like when you take a practice test and you get like 4 questions wrong, and then you take another one, you do some studying, right? You're like, oh, I'm gonna study the topics I got wrong on the practice exam, and then I'm gonna take another test. That's kind of the idea XGBoost has. But you might be wondering, can I only do this technique of making mistakes and then correcting it and making an even better model with just decision trees? Answer is no, you can do it with a lot of different types of models. But this idea of having multiple models together is called ensembling. It's like a musical ensemble, but with models. So we're going to go over a little bit of ensembling. We're going to go over simple and complex ensembling methods. And at the end, we have like a small example of a famous algorithm they use ensembling. So I have this example for you guys. Let's say that you hate school and you want to make an AI that does your homework, and like the classes that you're taking are like BME 3, Intro to Python, and I don't know, like calculus. Those are the 3 classes that you're taking. You don't want to do your homework, you want to make an AI that does it. Now that I've sort of told you the concept of ensembling, which is using multiple models, how would you go about solving this problem using that idea?
Just make one model that can each do a different type of homework, because odds are your Python homework isn't going to be nearly similar enough to like your calculus homework where one model can do both. So you just make multiple models, and then you make something that, maybe another model that over them that can examine the given, description of your assignment and then decide what type of homework it is and which model to pass the rest of the work to.
Exactly. That's also exactly a type of ensembling technique we have. It's called a mixture of experts, where you have a bunch of models that are really good at one thing, and then you have this model called a gating model that decides which model to use in a certain task. So it's a way to combine predictors for better and accurate models. There's a lot of classic ML problems or fields that you can use this idea in. It is very widespread. You will use this more than a normal decision tree. You can use this in healthcare. You can use this in mathematics. Anything that you know can be broken down into more and more tasks, you can use this idea in, which is pretty much anything. So the basic ideas, which are very intuitive, are voting, stacking, and mixture of experts. These are very intuitive ideas where if you think of ensembling, this is what will come to mind, even if you've never heard of it before. The more complex ideas are bagging, boosting, and ADA boost. Okay, this is our first slide. This is about voting. So I gotta make sure I don't miss any data, any words about this. So this is again a very intuitive idea where when I told you you need to solve this problem, I need to use multiple models for it, right? If I told you that you need to do that, you might think, okay, I will put multiple models together trained on the same exact data, or just multiple models together, maybe on some subsets of data, one trained on each feature, for example. And then I will ask them the same question, and they will all give me some result. And then I will take those results and just count which one I get, and whichever one there's the most of, that will be my answer. That is the idea of voting. Let's say that I have the question, who is the president of AI Club? I have 3 different models. I have Jasmine, Shreya, and Mun. And I want to know who's the president. And these models output, those outputs Queen Julia, King Julian, and Queen Julia. They all outputted 2 different things. And you can see here, Queen Julia got 2 votes and King Julian got 1 vote. That means that Queen Julia is the president of AI Club. Another way of thinking about this, I think makes sense to me, is let's say you're doing your homework. Even though your professor says don't compare answers, you're going to compare answers anyway. And what you're going to do is you're going to ask your friend, hey, what did you get for this question? You know, choices are A, B, and C. Friend says, I got B. Now, you know your friend doesn't go to lectures that much. You got the answer C. You don't know what's right. So you got B, I got C, what's the answer? If you ask 2 more of your friends, they say C. So you're like, okay, the answer is C. That's what the idea here is. That you have multiple models put together and you run them multiple times, or you could run the same model multiple times too. That's also an option. It doesn't have to be 3 different models. It could be the same model 3 times as well. And you didn't just take the majority. So you see I have this equation here, and I have this over here. So this idea of taking the majority is typically what you use in classification problem. Do you guys remember the difference between classification and like regression problems? Who remembers the difference?
Well, classification is categorical, and then regression is numerical, right? Where regression, you're trying to fine tune a number, and classification is just like, give me this, what is it? Pick a category and put it there.
Exactly. Yeah. So this would be the classification approach, where you just have some discrete class label, so you would do the majority voting technique. Versus for something numerical, you could take the weighted average of what your models output. Okay. Next, we have stacked ensembles. This is similar to voting, except the main idea is that you have a predictor trained on other predictors. So the idea is I have some data set, and in this case, we're going to think about it as a blueprint of a house. I want to live in a house, obviously. And so I have this data of everything that I want to do in my house. I need somewhere to sleep. I need somewhere to sit and do my work. I need somewhere to go to the bathroom. I need somewhere where I can host people. I have all these different things that I want to do. And you train multiple different models on this data set. So in this case, for a house, you can technically live, do work, even go to the bathroom if you think about it, in any room of your house. Even though the last one is very disgusting. I could live in my garage if I wanted to. I could live in the garden if I wanted to. I could live anywhere if I wanted to. Each one of the models that you train makes some assumption about your data set when it gets made. And then these are called their base models. They're the base, they're the foundation of the better, bigger model you're gonna make. And based on the outputs of these models, you train the meta model. And this puts all of them together. So it's similar to like a multi-layer perceptron. Were you guys there for last quarter's neural networks and perceptrons lecture? Who was there? Who came to the meetings last quarter? Raise your hand. Okay, that's okay. A perceptron is sort of like it's just a very simple line. Y equals mx plus b. That's basically what a perceptron is. It's a linear classifier, extremely simple. It's made of one neuron, which is a perceptron, and that's it. But if you put multiple perceptrons together one by one, you can get sort of these layers together. And that's sort of what the idea of stacking is, right? You have multiple things where the output of one leads into the other, and that's sort of how you connect these together. So level 1 is the base model, the models that fit on the training data and whose predictions are compiled to make the meta model. And that's the model that learns how to best combine the predictions of the base models to make the final model. The data used to train the base models is the actual data, and the data used to train the meta model is the outputs of the base model. If you visualize that, you could think of it as like a row of circles as your base models, and they all have arrows that lead up to one big circle, which is your meta model. So does that make sense? Any questions so far? No questions? Okay. Next, we have mixture of experts. So the basic idea is to take a predictive model task and break it into pieces. This is a divide and conquer approach. You break this problem, which in this case could be like building this Lego car, into smaller subtasks. And you train a model for each one of the subtasks. You need something to build you don't need to build the wheels in Lego, but let's say you did. The wheels of the car, something to build the door of the car, the hood of the car, the top, the seats, different parts. One model for each one of those things. And then you have a gating model that knows which model to trust for each one of those tasks. So in this case, this is like your task is to build it. Your subtask is say make a wheel, and you have to know which piece to choose. Which piece do you choose to make a wheel? You want to choose the wheel piece. You don't want to choose the like 2x2 Lego brick to make the wheel. It's a terrible piece for the wheel. Your car is not gonna run. That's what the idea is here. Task is to make a car, your experts are the pieces, and your subtask is make a wheel, make a door, whatever. This raise your hand if you've taken like data structures and algorithms, ICS 46, or if you're taking it right now. Okay, you'll learn about this in 46, about different types of algorithms like divide and conquer approach, the greedy approach, stuff like that. So now you're wondering, a very obvious question, how do you split it into subtasks? How do you know what I need to split by? That is like domain knowledge. You have to do that yourself. You have to know how to split it by. You have to know what your data is. And so you know how to split it. That's the main thing. So in like the Lego example, you have to know you have to build a wheel in a car. You have to know you need a door in the car. The expert, now let's talk about like the actual models themselves. The expert models, which are the smaller ones, they can be neural networks to predict or some linear regression models for numerical stuff. Really, the expert models can be anything. They can be anything that solves your problem. The gating model, the one that chooses which one to trust, that is traditionally a neural network. And the gating model and experts are typically trained together. Think about why you would do that. Why would you train both of them together? When the expert model makes some errors, and when you see what the expert model can and can't do, the gating model is able to learn that as well. Which one do I trust when? When I give this expert model this output, it was wrong, versus this output, it was correct. And the gating model takes that information, and that's how it is trained. The final output, there, I was like, I feel like I have another slide, but I don't remember. The final output is just a very simple thing of just selecting the expert with the largest output, or whatever the confidence of the gating model is. The gating model can say if I choose expert one, I think that it says to use the wheel piece, its probability is 90%. I use the door expert model. It said I should take the 1x4 Lego brick, and its probability of being correct is like 20%, right? You can take that and just say, okay, this one knows it the best. Let's just go with that one. So far, these are the simple ensembling techniques. Does that make sense to everyone? Does anyone have any questions on the simple ensemble techniques? No? Good? We'll go on. Now we're gonna go on to complex ensembling. Now let's say you're given a data set and told you need to train a diverse amount of classifiers. How would you do this? When I say diverse, I mean you need to train multiple classifiers, but they need to be different from each other. How would you do this? Think about it. I gave you a data set. I said, I want 5 classifiers. They cannot be exactly the same. What would you do? It's not a very simple answer to it. Like it's not, don't overcomplicate it. I just give you a data set. I said, I want 5 classifiers. They each got to be different. I have 100 data points, 2 features. You could just take 5 random samples of the data set and train 1 classifier on each. They will be trained on different data. They will be different from each other. If I have 100 data points, I want to train 5 classifiers. I just take a sample size of 20 for each, and I train 1 on each. Yes.
This seems like a job for voting.
It is. It could be a job for voting. That is true. But there's also we're gonna take this and put into another type of idea called bagging, bootstrap aggregation, where you make subsets of your data set with equal. Oh, the typo says equal tuples. Just equal amounts of tuples is what I meant to say. You take your entire data set, make 5 random subsets of it, and make a base model trained on each of these subsets. Each model is learned in parallel. Keep that in mind because the next one we're talking about is similar to this, but they are not trained in parallel. When they're trained in parallel, that means that they're independent from each other. Parallel means they don't have any relation between each other. They all have their own small part of the data set. They're all trained independently. They all have their little thing. And because of this, each train set is independent, each classifier is independent. We have a diverse amount of classifiers. The final predictions are determined by combining the predictions from all the models. So now this can be like a voting approach. You can say take the majority, you can say take the average. The main thing about bagging is the way that we train the base model. A famous example of a bagging model is random forest. So random forest is just a bunch of decision trees all together. You start by randomly sampling the data. You learn a decision tree for each sample that you take, and then you say that there's no max depth. It's very flexible. That means each decision tree is extremely flexible. This means that the learner is going to have, there it is, okay. Randomly sample the data, learn a decision tree for each data set. Bias, look at the definition at the bottom. I'm never going to talk about these questions. Bias is the error caused by oversimplifying a model. Variance is the error caused by making the model too sensitive to training data. Variance is like overfitting. Bias is like underfitting. So this idea of random forest, is this low or high bias? So I'm asking you, taking this approach, does this lead to a very simplified model that doesn't properly model the data? Or would you say that this is a very specific approach that models the data too well? You guys can just guess. Just say anything. You could say low or high. You're 50% chance you're right.
Low. I just say low.
Yeah, it is a low bias. It's a very simple approach. This is you're splitting the data across a bunch of trees. You are undersimplifying. You are not overfitting the data, which leads us to the next question. Is this low or high variance?
Low.
It's gonna be low because the model is very insensitive to the training data because
Yeah.
it's not super overfitted.
It's like overall, I think I mixed it up.
Wouldn't it be high bias if it's a simple model?
Yeah, I think I switched up the definitions. I think it's low bias and high variance. Or,
I thought it's high bias, low variance. Because
yes,
the more
low bi-
bias,
yeah.
the less flexible your model is because it's not overfitting it.
yeah, this model does not overfit. It reduces overfitting because by taking the data and putting it into a bunch of different trees, you're not having one mega tree of like a depth of like 100 that's extremely sensitive to the data. This is less sensitive to the data. So high bias, low variance. That's what I meant to say. Yeah, so it's high bias, low variance. And so this is a good way to reduce overfitting when you have data, especially if you have one decision tree that has a training accuracy that's very high and a test accuracy that's very low. That's like a telltale sign that you're overfitting, and you should try using a random forest. Okay, next we have boosting. You guys remember the one gorilla versus 100 men meme on Instagram? Raise your hand if you remember that meme. Okay, good. So this idea is basically how boosting works. If I had one man and one gorilla fight each other, who's gonna win? The gorilla's gonna win. But if you have 100 men, they might beat the gorilla. That's sort of like how boosting works. Boosting is taking a weak model and then sequentially training a bunch of weak models, one after the other, correcting the mistakes the previous one makes, so that you can potentially beat the gorilla or, do the task correctly.
So in this case, 100 wrongs do make a right.
Exactly.
Okay.
The way that boosting works
You might break it.
is you make of the model. This is how XGBoost works. This is the concept of boosting. You make a model on all of the training data. This model is gonna make mistakes. So typically what we'll do, like for XGBoost, for example, you train a decision tree that's just a stump, which means it has a max depth of 1. It gets to have one way to split everything, that best feature, and that's it. So they're gonna do badly. But you look, where did it do badly? What data points are causing the errors? And you add more weight to those data points, which means on the next iteration, you have more weight on those ones. You're going to correct those mistakes in the next iteration. You keep making mistakes, but as iterations go on, you correct those mistakes along the way. Well, I already answered the question, but you assign weights increasingly on the stuff that's wrong. So the next model learns from the weighted data set and focuses attention on the harder to learn examples. This all repeats until you have some max amount of models, or the entire data set has a training accuracy of 100%. So boosting is prone to overfitting because if you have too many of these models, you're gonna get something that's extremely overfitted to your data. So if you have XGBoost, if you're using XGBoost, don't make like your max number of estimators like 100. You want to use a lower amount, like 10 or something. So this is like a very useful approach in that it allows you to, if you have a very if you have a data set with a lot of variance, this is a good approach for that. Let me see how much. This is a very famous type of boosting algorithm called ADA boost. So ADA boost is famous because it sort of combines the idea of bagging with a little bit of boosting. And it has a very smooth convex cost function. Who remembers what a cost function is? What's a cost function in a model? Also known as the objective function or the loss function. So when you have a model that is being trained, let's say like a line through a data set, and you want to know what my best fit line is, how would you know? When you draw a line, if I give you a if I give you a graph that had a bunch of points on it, I asked you to draw a line, how do you know what the best line is? You're gonna look at it and do what when you draw your line? I give you a graph, points on it, I ask you to draw the best line.
Find the best fit.
Find best fit. And how do you like visually see that this line is good?
It's got like a relatively even looking amount of points on one side versus the other side. of
Yeah,
the
yeah, you want your line to have a relatively even amount on both the sides, and you want them to be as close to each of the points on both sides as possible. You want to reduce the residual between your prediction and the actual amount. So measuring the residual right there, that is a loss function right there.
Is the line called the least squares regression line or something?
Yeah, exactly, yeah. Like that's what the best fit line is. You want to have the least amount of loss if your loss is being wrong. You want to reduce how wrong you are. That's what the loss function is. And if do you guys remember gradient descent? Raise your hand if you remember gradient descent, or you know the concept of it. Right? When you do gradient descent, you take the gradient of your loss function. The gradient is basically the derivative, it's the partial derivative of your loss function with respect to your parameters. So if my loss function is something ridiculous and very, very hard to take a derivative of, how would you feel about that? You would be like, not good, right? That's hard. If your function, that's your function, you can't even take a derivative of it. You can't even take the derivative of your loss function. What do you do then? It could be a great loss function. You just can't take the derivative of it. You can't use it for gradient descent. But ADA boost is good because you can. The derivative is smooth and convex. Why is that good? Why is a smooth and convex loss function good?
Because that way it's easier to fine tune over time. You can, if it's smooth and rather than all discrete looking, it's easy to narrow yourself into a little zone and fine tune your boosting model over however many 100 dudes that you're boosting it over.
Yeah, exactly. That's exactly right. If your loss function is smooth and convex, the whole point of gradient descent is to find the best set of parameters for your model. The set that reduces your loss, the minimum point of your loss function. Raise your hand if you're taking calculus 1. You remember calculus 1? Do you remember like they ask you to take the derivative and find the minimum? That's exactly what gradient descent does. And if your derivative is smooth and convex, it is super easy to find that point that has the smallest loss and the set of parameters that correspond with that point. So when we say that ADA boost is great because of smooth convex function, it means that if you train your model using this algorithm, you will have a great model that you can quickly train and will be very accurate. I don't know if we went over this, but if you have a loss function that you cannot take the derivative of, you have to use something called the surrogate loss function, which is a fake loss function that is modeled as closely as you can to your real loss function. You use that sometimes for like perceptron learning, I think. They are very useful, but if your original loss function is perfect, then it's like you've struck gold. Like it's great. Is what I'm saying. So like you can tell here that the idea of ADA boost is like the teacher focusing on the weak learners to bring up the academic performance of the entire class. If like if I don't know, 28% of the class is getting hundreds, but 80% of the class is failing, what ADA boost does is like it looks for the parts that are wrong or the people that are failing, and then works on it, giving them more attention so that they do good, which brings up everybody's average. It is the most famous boosting algorithm for this reason. And you can see that here. So here's your original data set, and you look at the ones that are like right on the line that you're wrong about, or you could be wrong about. And at the next iteration, you update those weights. You give them more attention so that they're corrected more. Yeah, and a very famous example of raise your hand if you guys know about the Viola-Jones face detection algorithm. This was like one of the first face algorithms or like facial detection algorithms that came out. Raise your hand if you heard of like convolutional neural networks. That's like the most famous thing that's what you think of when I tell you detect face. That and like YOLO V8, for example, that's another one. You only look once. Those ones are also famous. This is famous because it is not that computationally intensive as a CNN is, and it uses ADA boost. So the idea behind this classifier is puts a bunch of weak ones together, and these weak ones are called Haar wavelet classifiers. It is those tiny rectangles you see right there. You're like, what is this I'm looking at? This rectangle thing. Does anyone have any guesses on what this rectangle is doing? Yeah,
Telling us which pixels are important.
basically. It just takes a rectangle and it says yes face or no face. That's literally all it does. That's all a Haar wavelet does. Yes.
Is it called ReLU?
ReLU is something that you use in your training of a neural network. This is like a type of classifier. It's like a perceptron, but like super simple. It's like yes or no. Yeah.
Is this tied to like computer vision and like how computers like when they scan like live video or imagery, they try to like use like the models that they're trained on to like kind of figure out if it's like it matches a certain face or not?
Yeah, basically, that's what this thing is doing. It takes these little rectangle parts. That's what it's trained on. A bunch of these little rectangles that are told, yes, this is part of a face, or no, it's not part of a face. That's all it does. It sections off this face, looks at it, and asks it yes or no. And then based on this this sort of conglomerate of a bunch of these yes no Haar wavelets, based on that, it says yes, is there a face or not. So it is a little limited. It can only really work on faces that are like facing forward. It's like a big image of the face in the picture, and they basically have to look like how this woman's face is. That's like kind of like the disappointing thing, that has to be very specific on it. But it's a very simple, intuitive idea. You have a bunch of these small rectangle things. Based on whether or not they say there's a face in it, you decide whether or not there is a face in this picture. It sort of speeds up and fixes the weaker binary Haar wavelet classifiers, and that's how it sort of decides what's good or not. And this is great because the base classifiers are very easy to calculate, because like the white area is subtracted from the black or gray area, and that's the part that we focus on, so the middle of the rectangle. So in this case, it would be the eyes, so it'd be like, yes, that's part of a face. Versus something that maybe be in this corner would be a no, because that's just blank space, that's not part of the image. And that's sort of how it works. So we're gonna go on to the coding example. We have a lot of time. Do you guys have questions on ensembling? No questions? Okay, then we will go on to the ensembling to classify types of wine. So what we're gonna use, I can share the data set. Scikit-learn comes with a bunch of toy data sets. Probably the most famous one that your professor is gonna keep using is the Iris data set, because it's the first one that always pops up. It's the one everyone uses because it has a lot of features in it. But I thought this one was pretty neat because it's a very interesting data set. Basically, it has 13 features, which are all different attributes of wine, and it predicts which region of Italy a wine comes from. That's what these classes here are. These are all of our features. You can see the instances. We're gonna use bagging and boosting in this example. Okay, who remembers bagging? I just talked about it. What's the difference between bagging and boosting? Which one is parallel, bagging or boosting? Bagging. Which one's sequential? Boosting sequential, yes. Let's load in our data. So even though we just looked at it from our webpage, it's really good practice that when you get any sort of data, you look at it, you look at the feature names, you look at the target names, you look at how big the data set is. We say this because there have been times where you will load in a data set and you're like, why isn't this working? And it's because your data set is either wrong or there's nothing in it. Even though it sounds silly, it does happen. So we're gonna get our data by using scikit-learn's data.data, get our target values by data.target, and we do a train test split. This is standard, 20% test size, 80% train size. That's how it always is. So we're gonna use decision trees as our base model. Decision trees are prone to overfitting when trained on very small data sets. Good thing for us is this is not a small data set. It has a size of about 178. But the thing about decision trees, as you guys know, is that like, you know, even if they are, yeah, they get overfitted. So we're gonna fit it. This is our parameter. We use Ginny, we use the best splitter. After we finish this, I'm gonna go ahead and play around with some of these parameters just to show you guys how interesting that they come out to be. It is very fun. The accuracy of the base model alone is about 94%. Makes sense. Then we're gonna use the bagging classifier. So what the bagging classifier is basically gonna do is it's gonna take the base classifier that we just made, make 10 of them based on a random subset of the data set, and then it's going to fit it. So you can make more than 10. Remember that the whole point of bagging is that each one of the classifiers is independent, so you don't have the problem of overfitting. The problem that you do have is underfitting, where if you make 178 decision trees in your bagging estimator, you're going to not have very good accuracy because that means each decision tree is gonna get one row of data to train on, which is horrible. That would extremely overfit it actually. So these are our parameters. It's the same one as before. That's the type of estimator we have. Oh, I already saw it. The accuracy is 97%. That is better than what we previously had. Why do we think it's better?
So fitted.
Yeah, now it's not overfitted. Now it's doing better on the testing accuracy. We can use ADA Boost to do the same thing. Scikit-learn has scikit-learn.ensemble, which the ADA Boost does. We're gonna load it again. Now remember when I said earlier that typically when you use boosting, you want to have the worst classifier as your weak classifier. So in this case, what we're gonna do is we're going to have a decision tree stump, which has a max depth of 1. This is gonna act as our weak learner that you need for ADA Boost, which iteratively improves by combining a bunch of these weak learners. So our base classifier is gonna have max depth of 1. Not a good accuracy. The accuracy is like about 67%. So the base classifier is going to use this weak learner, just like we did in bagging, for the purpose of doing it better. And now the estimators, we're gonna have 50 of them, which is more than bagging, which also makes sense because it's the number of like iterations that you think you're gonna need to have a better model. I will play around with these numbers after. Next one is the learning rate. Learning rate is used everywhere. You're going to use this in normal like neural network models as well for gradient descent because learning rate, or I think it's mainly called learning rate. It's like the alpha symbol. You use that to sort of determine how big of a step you take in gradient descent. Because if you have like a nice function in gradient descent in your like loss function, you have to decide how big of a step you want to take to reach the minimum. So this is called learning rate. It's sort of like how much each weak learner contributes to the final model, right? Train it. Actually about 97%, just like we did last time. But again, it's a lot better than just a stump. So we're gonna do a little bit, well, let's change some values instead. That'll be fun. Let's say we do 178 estimators. What do you guys think? Let's do 100 estimators. What do you guys think is gonna happen? Is accuracy gonna go up or down? Ooh, it went down. Now it's worse than the decision tree. Why did that happen now? This is the bagging one, by the way. Now we have 100 estimators. Why did the accuracy go down?
Underfitting.
Yeah, pretty much. In this case, like each decision tree has such like little data, it's not contributing to the actual thing anymore. Estimators here. Same issue. This case would probably be overfitting because we are trying to make it too good that our test data isn't representational anymore of the training data. It's thinking about it too much. What are other interesting things we can do? I think there's other features in this for sure. Yes. Max features again. Random state, warm start, number of jobs. But yeah, that's increase the learning rate. if you give each classifier too much weight as well, that's not good. Okay, but now let's do the review. In ensembling, what is the primary purpose of combining multiple models? Why do we do ensembling?
Greater accuracy.
Yeah, it's because we want to improve the predictive accuracy, we want to improve how well the model performs. Next, which ensemble technique is specifically designed to improve the performance of weak learners by sequentially correcting errors?
Boosting?
Yeah, it's boosting. How does bagging reduce overfitting in models?
Randomness.
By doing random subsets. What does a meta learner or a meta model refer to? We talked about this when we talked about stacking. What does it do?
It's like, it takes all of the other, it's like the model that encompasses all of the other models, where all of the other models are like ribs in the house, and then the meta model is like all the walls on the outside.
Yeah,
And it sort of combines all of their outputs into one output that's like cohesive.
no, exactly. That's exactly what it does.
Okay.
It puts all the outputs together from all the base models to create the final one. And what does stacking involve? What did stacking do?
Train on other vectors.
Yeah, it trained the new model by combining the predictions of all of the base models. That's what it did. Okay, do you guys have any other questions on ensembling? No other questions? It all makes sense? Okay, we have some announcements by, oh, that is the wrong slides. About projects.
Yeah, so I just wanted to give a brief spotlight about one of our external projects this quarter. We have a collaboration with Cloud Compute, which was one of the YC startups from, I believe, summer of 2025. And they're giving us an opportunity to work with their team and as contributors, where they're trying to basically have students actually work on their project and make advances towards their system. Cloud compute is basically a way of, is a compute platform where they're allowing a bunch of different AI modules to run on a plethora of different platforms, including iPhones, Android, and like other systems that you wouldn't expect AI systems to be running on. And they mentioned how they had previous success with UCLA's Bruin AI Club, where they had students make huge contributions to their app, like implementing Whisper Flow into their workflow. And they ended up getting, a lot of the UCLA students got poached by Google DeepMind, OpenAI, and a lot of them also got full-time offers from Cactus because of their contributions. You'll be constantly mentored by their founder and their team, so you'll always have help available. I think this is a really great opportunity for anyone interested in actually in getting real world application with whatever skills you learn in these workshops or any other skills. This is a more advanced project, so you will get what you get or put into it. There's no like hand holding. It's like an internship where you'll be assigned tasks. It's, you have something that you want to develop for this team and you put it in, you work on it, you get help for it, of course, but it's mostly going to be all your work and you'll be basically spotlighted and given opportunities based on that. So if you guys want to fill out the application form here, it's also in our Discord and we'll post on our Instagram soon too. Applications close on Friday, right, Julian?
Yeah, right.
Yeah, this and all our other external projects this semester, our applications close this Friday. So feel free to check it out. And thank you, Shreya, for the workshop.
Does we have time left? I was like, I'll go into sort of what we're doing next week. Let me see. I think next week is clustering. Yes, clustering. So first, I'm just gonna do a lot of stuff verbally about this, and then we'll go more in depth about it. I just want to give you guys an overview since we have time left. We're gonna talk a little bit more about unsupervised learning methods now. So the whole point of unsupervised learning versus supervised is that we're trying to find patterns now. Like, you guys remember, how would you sum up supervised learning in one sentence if you had to? What would you say it does?
We know the answers and we're grading it based on those answers.
Yeah, you know the answers. I want an answer based on something that I have found in the world, and you have to tell me the answer. That's basically what supervised learning does. Unsupervised learning is sort of like, I have all these observations about the world, and I want to see if you can find a pattern about it. For example, the idea of clustering is that I have all of these data points, and I'm trying to see, is there a correlation between them? Is there an example that a lot of these points lie here, a lot of these other points lie in another area? That's sort of what clustering does. I can show you an example of that here. This image here was created using a dimensionality reduction technique called UMAP. And UMAP is a way that you can take something that has a lot of dimension, a highly dimensional data, for example, embeddings, right, LLM embeddings, and be able to map them down into some sort of 2D form. So this picture here is a bunch of points of 99 random math problems from the Hendrix math dataset. And a LLM was queried and asked those math questions, and an embedding was made of them. And the idea here is to see if the LLM can answer these questions, first of all, and second of all, does it know which type of math problem this is? If you guys know how LLMs work, it's that their brain is basically a bunch of embeddings. For example, if I ask you, are cat and dog similar? You'd say, yeah, they're similar. Are cat and strawberry similar? Not very much. A LLM does that similarly, but using something called embeddings. And so what this basically is showing is that based on these different types of problems that the LLM was asked, these embeddings are generated, and intuitively you would think that pre-calculus problems, orange ones, all the orange ones would be together, pink ones would be together, brown ones would be together, green ones, etc., would all be together. You see, for the most part, they kind of are, but here and there you can see there's some mix-ups. There's some brown and orange ones here. There's a brown and red one here, brown and purple one here. But the main thing I'm trying to get at with this image is that when I make this, I'm not trying to look for an answer. I'm not trying to ask it to predict something. I'm asking it to look for a pattern. And that's what all of unsupervised learning is. Every technique you do in that sort of part of machine learning is for that question. What's interesting about this? So clustering just intuitively just describes the data by different groups, and the meaning of groups also depends on the data. You could think that, are we looking at things by location, by shape, by density? It all depends. There are three main types of clustering: K-means, Gaussian, and agglomerative. So who remembers, did you guys do statistics? You guys remember normal distributions? That's sort of what the Gaussian mixture models, which are probably the most interesting, are about. So K-means clustering, it's a lot of words here, is a very simple algorithm. You basically just have a bunch of data. You assume that each one is going to have its own cluster. You have 3 data points, all of them have their own cluster. And then you randomly choose a certain amount of centroid between all those data points. And those are gonna be your K, like, how do I put it? Like the middle grounds, the averages between those data points. And then at each one of those average points, you reassign the clusters, and you keep doing this until you've gotten the amount of clusters that you want. So if you have 3 data points and you want to have 2 clusters at the end, you would just randomly assign 2 clusters, and then between those groups, you would put together some centroids and then reassign them. We'll go more in depth about this next week with more visuals and stuff like that. So for each cluster, you calculate a new centroid, and you keep doing this until you found basically a like set of clusters that are no longer changing. They're the same. So manually, it's like you're assigning the points to their closest centroid and you're applying this until you're done with it. But you're thinking like, how do I know what closest means? There's a lot of different ways to measure this. There is Euclidean distance, just measuring square root of x1 minus x2 squared plus y1 minus y2 squared. There's a lot of different ways to go about this. You can also use root mean squared error. Or you could just subtract each one of the points, whichever the smallest number is, you can just say that. Now, what if you had a data set that was both like shoe size and shoe color? One of these is clearly categorical, so what would you do about that? What you can do is you can take different pairs of them and then assign them some sort of value. And you keep going about that, and that's how you sort of like semantically create distances between like words. Another thing you can do when you have like words like this is you can make those words into numbers as well. You can make them into vectors. There is a type of model called like word to vec. It's one of the original like sentence transformer type of models that you can take, and then you can have numbers, and once you have numbers, you can do whatever you want with numbers. So much easier to find if numbers are close by than words. Evaluating results. This is important because you're like, okay, well, clustering is unsupervised, so how do I know if my clusters are actually good or not? There's a lot of different ways to go about this, and you can use the quality using things like cluster cardinality. How many things are in your cluster? If you have a very big data set and for some reason you have a cluster with only one value in it, then that's a problem. Maybe you are overfitting your data and you have a high K value, too many clusters. Or maybe you have a cluster with way too many points than there should be. Cluster cardinality is a good way to check that. Yeah, so you can keep doing that, change the number. And so the main thing about k-means clustering is that you need to know the number of clusters that you need beforehand. And so you might be wondering, how do I know what the best value of k is? I don't know that. I was thinking the algorithm would tell me that. You can run multiple iterations of the algorithm, just increasing the number of k, which we'll do a coding example next week doing this. And then you can see what the cluster magnitude of each is. And whichever one is like the best, you can just say, hey, that's the number of clusters I'm gonna have. So we'll go more in depth about this. I think that there's like 13 pages. It's gonna be a big next week, because I was like, if I just go over k-means right now, it's less to go over next week. But yeah, I mean, any questions on the little bit of k-means clustering went over right now? Okay. And we said we're gonna ensembling. I think that's pretty much it. We are good. Okay.